We saw in the last video that the solution set to a homogeneous linear differential equation is going to be a vector space, and the dimension of that vector space is going to be the order of the equation. So if we happen to stumble upon some solutions, and we'll talk about more specifically how to find particular solutions later, but once we've got a few solutions, we need to know, do we have enough, right? Do we have a spanning set for the entire solution set? Are they linearly independent, right? If we have 3, but we only really needed 2, then maybe we can express one as a linear combination of the others, and we don't really need it. So those are the two questions that we have. And what I want to talk about in this video is how to use the Wronskian to answer that question. The main result about the Wronskian, which I called the tattoo, or the theorem about the Wronskian, this says that if I give you k functions and the Wronskian is not 0 even at a single point, you only need a single point for the Wronskian not to be 0 at, then those functions are linearly independent. If you were reading the book very carefully when we first talked about the Wronskian, the book makes this comment that says you can't go the other way. In other words, checking the Wronskian allows you to conclude that things are linearly independent, but it can't be used to conclude that those functions are linearly dependent. Why might you think that? Well, you might think the following is true. That is, you might think that if I compute the Wronskian and I know that it vanishes, meaning it's 0 everywhere, then I can conclude that the functions involved are linearly dependent. And the thing is, that's false. It's tempting, but it's not true. So I'm going to go ahead and cross it out. Okay, so that's kind of a problem because, when we're checking a set of vectors, we want to be able to conclude, sometimes we need to know that they're linearly dependent. Okay, it turns out that there's sort of by this miraculous stroke of luck, there is a nice fact about the Wronskian as it relates to solving linear differential equations. If you happen to know that the functions you're testing all satisfy the same homogeneous regular differential equation, and that thing has order k, the same number as functions as you're testing, if the Wronskian is 0 everywhere, then in fact you can conclude that those functions are linearly dependent. Our chief concern here is solving systems of linear differential equations, which means that actually the Wronskian is pretty fantastic for us. So let's work that out in a particular example. We're going to consider the equation y triple prime plus y double prime plus y prime plus y equals 0. If we were to rewrite the linear operator associated to that, it's going to be d cubed plus d squared plus d plus 1. That's a linear differential equation. It's regular. The coefficients are all 1, so they're continuous. So you can check that these are in fact 3 solutions of that particular differential equation. Maybe pause the video and verify it for yourself. I'm not going to go through it. We have 3 solutions. This is an order 3 equation. So we've got 3 solutions. We're looking for a 3-dimensional space. The question is, did we find them all, or do we need to keep looking? In other words, I've given you 3 solutions. If they're linearly independent, we're done. On the other hand, if they're linearly dependent, that means we missed something. We got to find another one. So let's check it. Let's compute the Wronskian. Okay, so the Wronskian is this determinant. It's a kind of a big determinant. We could try to compute it by hand. It's a 3 by 3. We can do it. I want to make the observation, though, that if I label these columns as C1, C2, and C3, and I go ahead and do some column manipulations, let's replace C1 with C1 minus C3, and we'll replace C2 with C2 plus C3, and we're going to leave C3 alone. By doing that, we obtain this matrix. And then all you have to observe is that these 2 columns, the first 2 columns, are the same, which tells us that the determinant is 0. So what have we concluded? The Wronskian is 0. Normally, the Wronskian being 0 everywhere doesn't allow us to conclude that these are linearly dependent, but because they all solve the same equation, they all solve the same regular third-order linear differential equation, that test says, yeah, in fact, they are linearly dependent. You can actually see this directly. If you think about it for a minute, you can write down a linear relationship between y1, y2, and y3. But if we're not clever enough to see that, we can at least check that the Wronskian is 0. So what does that mean? I have a 3-dimensional solution set. I found, in this case, 2 linearly independent solutions. So y1 and y2 are linearly independent. That means I know I have to look for another one, right? So it turns out that the one we're looking for, I'll call it y4, is e to the minus x, and you can go ahead and verify that that works, and you can sort of glance at it and see that y1, y2, and y4 are linearly independent. So if we hadn't checked this Wronskian, we might have convinced ourselves that we found all the solutions, and we might have just missed out on finding that y4.